So when we're doing this, we didn't finish module 1. Oh, and I'm not sharing my screen. That doesn't. I think I finished it independently, Andy. I think what I did was, let me check the YouTube channel. Hold up. So, hold up. Classwork, module 1. Yeah, I finished it independently. So if you go here, I think this finishes it up. Why is this there? Okay. Yeah, it looks like I finished it up in this video. So it's out there. I was going to ask you guys if you guys wanted, because some of my other classes are going to start doing it this way. I filmed the videos on my own, and then class time will be more for if you guys have questions. Like, you can just type in the questions and I can go over it a lot more instead of just me rambling on what the tutorial is. Well, I'll ask this question when there's more of you in class, not just 2 of you. All right, so let's talk about double angle formulas. So again, you're gonna need the notes. You don't need the notes, but I do recommend having the notes because it does have the double angle formulas here somewhere. Where are they? Double angle and half angle formulas. Cofunction. There they are. Double angle formulas. And I think this one even has half angle formulas, if I'm not mistaken. It doesn't have the half angle formulas. You can derive it from the double angle formulas, but we'll get into that. The double angle formulas do kind of relate to the sum and difference formulas, and we'll get into that a little bit. So in this lesson, we're going to learn about the double angle and half angle identities. Wow. I don't know why Admentum started going into less detail. So the reason why we use double angle and half angle identities is to kind of figure out certain things. So if we're trying to figure out an angle, the y value, the sine, in other words, the sine will tell us how far something's going up, and the cosine will tell us how far we're going horizontally. So by knowing the angle of something and by knowing in this case, the velocity, this will kind of help us out. So by knowing these angles, it'll help us know the horizontal and the vertical velocity of something happening at an angle. So let's take a look here. So we're going to use, so these are our identities. Again, I recommend having your worksheet printed out or just having your double angle formulas printed out. You'll see here, they don't really repeat the cosine one. Cosine, double the angle of cosine can be written in a couple of ways. So they kind of have that written out here. So these we're going to derive from the sum formulas where we added these angles. We're going to assume that our alpha is the same. So instead of calling this alpha and beta, we're going to just assume that it's double alpha. We're just going to double that angle. So here we are. We're going to expand the sum, but we're going to assume that sine and alpha are the same. So when we're doing this, what I'm going to do, can I copy this? If I can copy this, that's going to be so awesome. I'm going to copy. Okay, I can highlight it. Can I copy it? Of course I can't. That would just make my life easier. Let's see. Control V. Kind of let me copy it, but not really. Okay, let's just I'm just gonna do it. So having this open, I can see that sine, it would be sine of alpha. Where's my alpha? Sine alpha, and then cosine of beta. But my beta just so happens to also be an alpha. So then this would also be cosine of alpha. And then it's going to be plus or minus. So sine is easy because sine has the plus sign. So if it's plus on the top, it's also going to be plus here. So if we're talking about adding, cosine's the one that's weird. If we're adding, it's going to be a subtraction. So here we're going to add these two together. Hey, Nick, thank you for joining us today. Hello, Nick. Can you hear me? Hello. I'm doing good. Thank you for showing up. Are you awake? Okay, cool. All right, so here's what we're doing. So we're just using the sum and difference formula. So we're using the sum. We're going to assume that these two are the same. So this is going to expand into this idea of sine of 2 alpha. That is a terrible looking alpha. I'm sorry. So we expanded it. Is that it? They just, okay. To derive oh, they want us to actually derive it. Okay. I was like, that's way too easy. So if we want to derive this double angle formula, we want to derive this sine of 2a formula. So if we think about this, let me go back into here. What I'm going to do here is we see that this is sine alpha plus sine alpha. So I can rewrite this. Rewrite this as sine alpha plus cosine alpha. So this becomes 2. We have 2 of them together. 2 of that. So that's all we're doing here. We're just taking our sum formula. In this case, the sum is sine of alpha plus alpha, not beta, equals this. And then we can just keep rewriting that over and over again. So we're going to reorganize it and do this. So this allows us to do certain angles that we wouldn't have been able to do before. I can't think of any off the top of my head because if you double any angle, you can pretty much do it on the unit circle. But you do need these double angle formulas to get to the half angle formulas. The half angle formulas, I think, are a little bit more useful. And the reason for that is, like, let's say we're doing sine of angle 15. You can actually use this to do sine of 30 divided by 2. And we'll get into these half angles soon. So this is pretty much simple. So that's how you know where this came from. You're literally just doubling, you're literally just assuming that your alpha and beta from the sum is the same. Does that make sense so far, guys? Cool. Nick, are you awake enough to understand? All right. Well, and here's an example of them using it. So we can do sine of 60 by doing 2 times sine of 60 times cosine, or sine of 30 times cosine of 30. Like I said, you can still do this in the unit circle. So I don't think the double angle theorem is as useful, but this does get you thinking of how to derive different trig identities. And I remember when I was in precalculus, I thought trig identities were interesting because you can use any of these formulas to prove anything else as long as you do the right steps. So first thing, derive the double angle formula for the sum identity. So first things first, we're going to assume that the angles are the same. So use... Okay, so step one, we're going to use... What? We're not doing it for cosine? Oh, this one's wrong because I put the plus. It's not the sum. Cosine. So cosine is a difference. So if we're adding two angles that are the same, we're going to do the difference. So that's how come that one was wrong. So I want this to be the difference. And then they show the outcome right here. So if I'm adding these two angles together, because normally it's alpha and then beta, but in this case our alpha and beta are both alpha, it just looks like we're doing the same thing. So then from here, so what can we do from here? So in this case, an easy thing is these are two different things multiplied together. So if these are two things multiplied together, you can just square it. It would be cosine squared minus sine squared. So simplifying by rewriting this, we can do that as cosine squared times sine squared. So these two are the same, being multiplied. How do we show multiplication? We use exponents. So that's how we can derive the first part of the double angle formula for cosine. It's double angle formulas. Double angle formulas. Double angle, double angle. I always forget where these are placed on here. Oh, double angle. So that's how we do the first one of the double angle for cosine. If we're doubling cosine, we can do it as cosine theta minus sine squared theta. So we're just squaring these. Later we'll see how we can derive these other ones. So here's how you can use it. Again, I always think this one's weird because it's like we can look this up on the unit circle, but this is a different way of getting into it. Another way of doing this is thinking about this idea of one. So this idea of one, let me show you what I mean. Remember how we're doing a unit circle? Well, a unit circle is essentially your x squared plus your y squared equals 1, because our radius is always 1 in the unit circle. Another way of saying this with the same thing would be cosine squared theta and sine squared theta, because we know that sine and y are basically the same thing, is equal to 1. Well, another thing we can do, instead of going sine squared theta plus cosine squared theta is equal to 1, we can also say that sine squared is the same thing as saying, so sine squared is the same thing as saying 1 minus cosine squared. So that's where they're getting this formula from. And then they distribute it. And by distributing it, we get this plus cosine here, which will allow us to turn this into 2 cosine. So we have 2 cosine squared. So that's where we get that from. We can also use this idea of, let me kind of split these two up because it looks like they're the same thing. We can also use this idea of sine squared plus cosine squared equals 1 by replacing the cosine. So if we replace the cosine, this is the idea of cosine squared theta is equal to 1 minus sine squared theta. So we're replacing that with the 1, and this, we're going to end up doubling this. We don't double the angle, we just double the fact that we have 2 sine squared alphas here. And if you guys are having trouble remembering these are actually known as your Pythagorean theorem identities. They're right here. So this idea of sine squared plus cosine squared, it's just the idea of what I just said. If we have a triangle in the unit circle, we know that our hypotenuse is 1, so it's 1 squared. So a squared plus b squared equals c squared. That's this whole idea here. And we know that our x value is cosine, we know our y value is sine. Does that kind of make sense? Usually I try using triangles when I'm teaching trig. I think it helps. Good, bad, something that makes sense? Mm-hmm. Okay, that's fine. He said he was having trouble. Okay. But does this make sense, everybody? Anybody need me to explain something? Yeah, it makes sense. Okay. Yeah, it makes sense. Or yeah, you need me to explain something. And as always, and as always, guys, you guys can always rewatch it on YouTube later. Um, Once Garrett gets back, I'll ask the question that I was asking Garrett and Andy. So now we're gonna derive it if the alpha and beta. So this right here is our sum formula for tangent. So where's some formula? Oh, there's the half angle formulas. So the sum formula for tangent is right here, except we're gonna pretend that it's that both of them are alpha. They're not different angles, they're the same angles. So the main thing you should see here right away is this idea of, well, if they're both the same thing and we're adding it, it should be 2 tangent alpha. And if these two are the same, it's going to be 1 minus tangent squared alpha because they're being multiplied. The one thing that always got me when I was doing trig is, why is the tangent squared? And the reason for that is it's the same thing as this. They just, I mean, I don't know the reason for it, but if you ever see a squared here, it's the exact same thing as saying tangent theta and then squaring it. Just for some reason, they like squaring the function. Oh, I guess that makes sense. They're squaring this function. So first you plug in your angle, whatever you get as a result, you're going to square that. So it's kind of like this idea of y squared. In order to get y, you have to plug it in x, and then you square this. So they're just like, we're just going to square the function of whatever you get. All right, so that's how you end up getting this part right here. So you just add it together and go. And then another way of doing this, so if we're doing this for cosine, double angle identity. Cosine. I'm sorry, guys. um, you can, you can rewrite this the other way using the cosine idea. So the cosine idea is, wait, where is the cosine? I don't know where they're deriving this one from. Like cosine, the tangent double angle theorem has two forms. I don't know how they got this form. Oh wait, hold on. No, I have I have no idea how they changed that to cosine. The only thing I can think of, so Adventum's just skipping steps, I feel, because they're like, yeah, totally, that works out. I don't see how that works out, Adventum. I can kind of, well, don't worry about deriving this. If they're skipping it, a lot of the deriving stuff is just so you guys can understand that they're just not making these up out of nowhere. So don't worry too much of the deriving, just know that it's possible. They might ask you a few questions on it, so you might want to review it. But for the most part, just know that you can derive them. So now we're going to do half angle formulas. This, I think, is a lot more useful. It's kind of the way you derive these is just by using the double angle formula, but we're going to double a half angle. So let's say we're doing the double angle formula for cosine. So if we're looking at the double angle formula for cosine, they're choosing to use the 1 minus. So they're choosing to use this form of it. And what they're going to do here is they're going to square this angle that's cut in half. So instead of, sorry, I know I'm going back and forth a lot, and the lag's probably like really affecting your monitors. So what we're going to do here is we're going to do 1 minus sine squared over 2. How do we get that? Well, we're going to do this, but because we're only doing half of the angle, we're going to divide whatever we get from this. And that's how we get that. And the next one. Why are they doing this so nonchalantly? I hate it when they just skip steps. They're just like, yeah, that's how it works. Sine squared. They just divide it by 2. I don't know why they're dividing by 2. Well, I know we're doing half the angle, so that's all they're doing. They're just dividing it by 2. Okay. Well, they're just going to skip all the important stuff. Like I said, these slides are just to prove you that it is possible. I don't like how they're deriving it. They're skipping way too many steps. But our half angle formulas are also saved up here. If you guys need them, all the half angle formulas are right here. And they also have alternate forms. I don't think so, because it looks like they're mainly focusing on the main form. That's a good question. I don't think so. The main difference between the alternate forms is that if you have it as a square, you can still derive it. But it's really simple to use. Okay, let's say I don't want to use the square root. Just square both sides. That's all they're doing here. They're just taking this and squaring it, and they're taking this and squaring it, and it makes it so there's no plus or minus. You're literally just squaring it. So you do kind of, you don't really need the alternate forms, no. Long story short, you don't really need them because you can just square both sides and get it. So that makes, yeah, just square both sides and you're good. Let's see. Maybe they'll say something different. Okay, so they want us to actually derive these. So I think that'll help out a lot. So we're going to derive this to derive the half angle formula. So if we want to derive this, I'm going to replace this A. I'm going to replace this 2A. I'm going to say that A is equal to x over 2. That'll kind of help us see this a little clearly. Or I'll call it alpha. That way we can actually see it. Yeah, I'm going to replace it with theta. Let's see here. Half angle. All right, let's get into proving this. So we already know that cosine of 2 alpha is equal to 2 cosine squared of alpha minus 1. So this is what they're throwing at us, but we want to do the half angle formula. So how do we get this? To derive the half angle formula. So this is a double. Then we're going to replace this cosine with this 2 of x divided by 2. And we're going to call that 2 cosine squared of. The reason why I divided it by 2 is it makes it a little bit easier for you guys to see that I'm cutting something in half. And then I'm going to subtract this by 1. So basically what I want to do is I want to get this cosine x over 2 by itself. So in order to do that, first I'm going to simplify this side right here. So 2 times this, that's going to be cosine of x. And then this side pretty much stays the same, unfortunately. So we get that. And then I want to get, again, my goal is to get this cosine x over 2 by itself. So in order to do that, I'm going to have to add that 1 to both sides. I'm going to add 1 to both sides. And I get just this part by itself. Now I want to get rid of this times 2. So in order to get rid of that times 2, I'm going to have to divide the other side by 2. So I have a fraction here. It's going to be divided by 2. And my laziness causes me to find shortcuts. So I'm just going to copy this. Probably wouldn't have taken me that long to write down. I get that. And this is going to be equal to cosine squared x divided by 2. Oh, doesn't do the fraction option unless I click it. Oh, yeah, he said he clicked on something he wasn't supposed to. Probably. Okay, so now I got rid of this times 2. So I got rid of the times 2. So now I just need to get rid of the squared. But let's say I didn't want to get rid of this squared. That's our alternate form. So remember how you asked about do we need the alternate form? The alternate form is a good way to kind of just be like, hey, I did it. Except instead of them dividing everything by 2, what they're doing is they're like, let's multiply by 1/2. But it's the same thing. So you can see here, it's the exact same thing. The only difference is because I'm doing a half angle, it canceled out. So it's pretty much the same thing here. It's just, it looks weird. Mine, oh, I see what's going on here. So mine is x divided by 2. Theirs is just 2 times that. So if I would have left it like this weird thing right here, it would have been fine. But this is also another form of the alternate form, just with a different theta. So now to derive the actual formula, so I'm going to square root these to get rid of the squared. So if I square root this, I have a plus or minus, because whenever we take the square root, you have to count for plus or minus. It's a fraction, so this is our cosine of x plus 1, and we're going to divide that by 2. And this is going to be equal to cosine of our half angle. So that's how they get the half angle formulas using the double angle formulas. Also, I could have left this as alpha. That way you can see it the other way. Oh gosh, there's so much stuff. Control Z. I would have left this as alpha, I could have done the exact same steps just a little differently. I won't do that. I like replacing it with x over 2. It just, to me, it makes more sense to call it x over 2 instead of leaving it in this weird way, because this is like, how is this a half angle formula? This makes a little more sense. So if you're like trying to find like 30, but you want to use cosine of 60, you can use it this way. So I'm just going to post it like this. They're probably going to show you the other way. Oh, no, they did it exactly the way I did it. This is, you guys need to remember this. This is probably like the first time me and Edmentum are on the same page. So yeah, everything's there. Even the plus or minus. Wow. The only thing me and Edmentum didn't agree on is I didn't rewrite it as 1 plus that. But I guess I could have. I could have just swapped these over when they did it. And to be honest, normally I do it. I was just thinking Edmentum's not going to do it. So yeah, this one, I'm going to give myself a 5. I actually understood what I was doing here. I think there's only one real way to teach the trig identities. So that's how come like it flowed easier for me, because I'm like, there's only one way to teach this. So now they're going to prove it for tangent. So in order to do tangent, what they're doing is they're kind of defining what tangent is. Tangent is y over x. So tangent is sine over cosine. So, and if you guys kind of need a refresher on that, it's this idea of tangent is, so if we do SOHCAHTOA, oops, I forgot the ka. SOHCAHTOA, if we looked at tangent, tangent could be this over this. So our sine, our so divided by our ka. And the reason why this works is whenever you're dividing fractions, you multiply it by the reciprocal. Oops, O over H times H over A. And that's how you get that TOA, that O over A. So that's how come it's sine over cosine. But now what they're going to do is like, we're going to do it for a half angle. So we can replace this angle with this. So if we're doing that, what they're now doing is our denominator is the same. So if our denominator is the same, so since both the numerator and the denominator are both doubled that, then we can cancel them out. So what they're going to do, they don't really show it, but they end up flipping this. So they flip this over to make it times the square root of, so it's a times symbol, square root of 2 over 1 plus cosine x. So that's where they get this from. You can flip stuff over in the denominator because it's a long explanation. It's not that long. I'll explain it. We can just say this right here is 1 minus cosine x divided by the square root of 2. So that's why they're able to just flip this. I was just lazy and I didn't want to write square root of 2 over square root of 1 plus cosine. That's just my laziness. But they're skipping a bunch of steps, so I don't think I'm being that lazy compared to them. And from here, what they're doing is they're like, let's just put it back in 1 square root. So that's where they get this idea is they do the half angle formulas, then they multiply the reciprocal, and that's going to give them this right here. And then after they multiply by the reciprocal, they're going to simplify it into 1 root. That kind of makes sense, guys. I know that's a lot. Are you guys good? Garrett, is your computer working okay? He said it's not. It's fine. Okay. So now let's derive it an easier way. I thought that wasn't that bad actually, but all right. This looks way more complicated. How is this easier in Mentum? We were on the same page one time. All right. So what they're doing here is they're being weird. What are they doing? Okay. So here's our half angle identity. And then take square root. So they're deriving another method. Let's derive an easier, less cumbersome model. So they think this is hard. So what they're going to do is they're going to make it, oh, this is nice and easy. What they're going to do here is they're going to eliminate this top portion by using, they're going to do this by using, what's it called? Starts with a C. Conjugate. There we go. They're using the conjugate. By multiplying the top by its conjugate, what's going to happen is this is just going to turn into sine squared. And let me show you why that works. If you were to multiply this kind of using the box method, 1 minus cosine squared theta, 1 cosine squared, or cosine theta. We get the squareds later. This becomes 1. This becomes cosine theta. This becomes negative cosine theta. So these cancel out. I know I'm using x's, but I don't want to write theta that small. So that's why I started using x's. And then over here, we get negative cosine squared theta. So that's where they get this from, is by multiplying it by the conjugate. This bottom part, these two are the same thing. So that's why they're squaring it. And remember our Pythagorean theorem identities? If this is 1, this is our sine theta. This is our cosine theta. So if we square it, we can just see this as sine squared theta equals 1 minus cosine squared theta. So they're just replacing this with sine squared theta. And then they're like, hey, guess what? Since this is squared, you can just take the square root of it and it just turns into sine, and this will turn into that. So that's how they derive this. Again, I don't know how much they're going to make you do deriving, but I would review this because sometimes on the mastery test, what they do is like, what part did they mess up on this proof? All right, so moving on. So now they want us to derive the third form. Geez, how many forms of this are there? There's only one on here. Jeez. All right. So to derive a third form, what they're going to do is they're going to simplify this. So they're going to try to simplify it even more by making it 1 minus it. So they're just going to multiply the bottom by the conjugate. And by multiplying the bottom by the conjugate, we end up making it where we get the sine. Because what ends up happening here is we get this 1 minus cosine squared theta, which again, I know I keep bringing this up, but it's a good way for you guys to make the connection on why this equals sine squared. And it's just this idea of this x squared, y squared equals 1 squared. So if we do 1 minus x squared, we're going to get that y squared. And y is the sine. So by multiplying by the bottom, we're going to end up getting this. And on top, we end up getting this part right here. Is this making sense so far, guys? Yes, no, maybe I'm going to have to watch this again on YouTube. Okay. Do me a favor. Also, guys, when you guys are rewatching the videos, if you notice that I forgot like one, because I forgot there's one that I forgot to record it, or I recorded it, but I recorded the wrong screen, so I just had to delete it. Let me know, like email me, like, hey, this video isn't up, and I'll start recording it. Oh, which brings me to my next point. We're gonna stop here for today, so I'll start. I'll start at slide 17 for today.